I'm Mike Micheletti, and I'm a product manager here for the USB testers at Teledyne LaCroix. We're going to take a real-time tour of the Voyager M4X, our USB4 and Thunderbolt 3 analyzer, which is really our flagship test platform for USB. Released in 2019, it's an analyzer, exerciser, compliance tester, and it's designed to cover every phase of the USB4 and Thunderbolt protocol verification process. It uses our TAP4 probe design, which is a fourth generation analog front end we use for tapping high-speed serial protocols. It's considered a linear amplifier, so it generates responses that are nearly flat from one input connector on the analyzer to the other. This means we can place the analyzer in the line without distorting the normal equalization sequence that occurs at power on. Plus, operating as a sniffer, it can capture all the tunnel protocols to help debug and verify correct operation of the USB4 link. The M4X is designed to support USB4 and Thunderbolt 3, plus all the legacy USB 3.2 speeds, including Gen 2x2, PD, Type-C. So this single platform is really designed to cover the next 10 years of USB development. The analyzer sits in line between a real host and dock using Type-C cables. Now, for testing USB4 and Thunderbolt 3, you need to use the Teledyne LaCroix cables shown. It's very important that one of our unmarked 40 gig cables are on one side. You can't use two regular Thunderbolt cables with an analyzer because then you would have two E markers in the line and you'll see collisions on the PD channel. Setting up the analyzer is very quick and easy. We're using Thunderbolt 3 devices here, as USB 4 is generally not available yet. And we'll run the USB Protocol Suite, which is a Windows application that lets you set up the analyzer. We first want to use the wrench to open the recording options. There we need to check USB 4 or Thunderbolt capture. It's also helpful to record the PD traffic, which we can enable here. We'll use Snapshot to capture everything from the point we connect the two devices. It's not required, but it's recommended to connect the host to the right connector. Optionally, it's helpful to also type in a name for each device, like dock and host, so that each event is labeled in the display. We'll use a large buffer, maybe 5 gigabytes, as we want to capture all the power on link training. Almost ready. Switch to the USB 4 tab. The user needs to specify whether the signaling is the USB 4 rounded or Thunderbolt 3, which is considered legacy signaling. We're using Thunderbolt 3 here, which is always considered legacy. This is one of the settings that we can't auto-detect, so the user needs to set it manually. We've just added an auto-detect mode for these other parameters where you can leave it in auto and the analyzer will automatically detect and use the correct settings. But it's important to be familiar with these. So I'll walk through them briefly. I know these are Gen 3 capable devices. Gen 3 always runs with FEC enabled. And if the devices are Alpine Ridge based, pre-coding is disabled. Once we get USB 4 devices, we should expect pre-coding will always be enabled for Gen 3. Filtering is critical in USB 4. Almost without exception, you always want to filter idles, skips, time synchronization packets. Usually I also filter the sloss ordered sets, which really fill up the buffer, but for this demonstration, we're going to instead capture the sloss one so we can see their role during link training. That should be it. Click OK to close the recording options. Go ahead and press record. I'll bring the link up by toggling VBus here. We see traffic below immediately fills the buffer and starts uploading the trace. Now, if you get red LEDs, the analyzer wants you to flip the cable to get a green LED. Just like our previous Type-C sniffer, we didn't want the USB 4 analyzer to use a MUX to reroute the high-speed traffic from the upper pins to the lower pins. Real devices do this. They handle a flip in the cable, primarily with a MUX or a switch. On the analyzer, that's going to introduce reflections, and at 40 gigabits, you want the cleanest signal possible. You're going across two cables, extra connectors, so any additional margin helps. Now the trace is fully uploaded. We're looking at real Thunderbolt traffic here from the host and the dock direction, Gen 3x2. We scroll up to the beginning, and on plugin, you'll see the initial Type-C states, where the host is toggling. When the dock is connected, it initially shows RD, so it comes up as the sink. The host showing RP comes up as the initial source for VBus. The Type-C controller would resolve any lane reversal here, and then establish which of the high-speed pairs will be used for lane 0. We see the first PD messages. The analyzer always shows PD packets on CC1.
vCon is always on CC2. Here we see the host actually doing discovery on the cable. Is the cable Thunderbolt or USB4 compliant? It's helpful to roll up these packets into transactions using the transfer layer button, which mostly just hides the good CRC. All the PD commands now appear back to back, so it's easier to read. We see the initial PD contract, followed by discovery of the alt modes. It supports DisplayPort and the Intel SVID for Thunderbolt. Scrolling down a little, we see the host sends enter mode. That will change to enter USB once we start seeing real USB4 devices. But the host now starts the link-up process for Thunderbolt 3. I'll hide the PD traffic with this button. So now we're just seeing the packets sent over the low-speed lines, or SBU. They get this SBU label. And the very first thing we see is the connect event from the host direction, where he holds SBTX high on all his downstream ports. The device router sees this and responds with the same. Again, we label this like a packet, but it's really just an electrical state change that starts the link initialization sequence. And this is followed by the first actual SBU transactions. These are administrative type, or AT commands, where the host sends read requests and then the response coming back. These are targeted at the SBU config space, and both the host and the dock will send these. The response shows that both sides are Gen 3 capable and will operate with FEC enabled. So these are the initial conditions the link will try to operate at.
We see LSE resume, also on the sideband. It's an LT packet type, sent initially by the host, which indicates that it's turning on its high-speed transmitter. Eventually the dock sends the resume as well, and only then do we see the first high-speed ordered sets. Both lanes start by sending back-to-back symbol lock ordered sets, or SLOS1. You may see an error or two here, where the first packet could be marked as an IPS or unrecognized interpacket symbol. That's the analyzer trying to lock on the high-speed traffic. Very quickly it does lock, and we see normal SLOS1 packets from both sides and on both lanes. So this is before the lanes are bonded. So we're in the transmitter training state, but you can see that if I unstack the traffic, there's a constant stream of SLOS1s filling up the display. So by default we stack the repetitive primitives. I can quickly hide all the high-speed traffic using the hide button. Now we're just looking at the SBU TX training messages, so only the low-speed traffic. Some of these packets are marked as errors. Thunderbolt devices will sometimes use fields that are now reserved in USB4, so disregard those. We can see both sides periodically issuing reads to the SBU registers, and it's the response coming back where the link partner is making adjustments to the far-end transmitter. Key fields here are new request bit going high, sent by the host. He's requesting a different preset, number 8. So it's the dock here that needs to adjust his transmitter accordingly. And it's the DFP at the far end that evaluates the signal. If he doesn't get lock, the process repeats with another new request. Once he sees a clean signal, he would assert the RX locked bit. Jump to the end and we should see the RX locked bit asserted on both sides. So that's when the TX training is considered complete. Here the dock is reporting locked for both lane 0 and lane 1. The host actually reported locked earlier. I'll double click on that one where the host shows locked and then unhide the high-speed traffic. Bringing back all the high speed, we should see the TS1 and TS2 handshake, which initially will complete in a single lane. Thunderbolt and USB4 will both go into this interim state where the link is trained, but now the connection manager wants to configure the router before entering the bonding substate. He'll come back later and configure the 2 lanes into a dual lane link. To make it easier to view the configuration process, we can use Hop ID to filter the trace and view just the control traffic. Control packets are always addressed to Hop ID 0, so I'll filter out the other Hop IDs, apply, close. Now we can see just the high-speed control packets. Host is doing discovery on the router config space. He's reading the basic capabilities. We see the max adapter is 13, so that's how many lane and protocol adapters he needs to configure. The very first write command assigns the topology ID and sets the valid bit. So that topology ID of 3 is now used to direct packets to this specific router. Scrolling through, we see mostly reads where he's discovering all the router's capabilities. A lot of VSC or vendor-specific capabilities in Thunderbolt. Eventually, we'll see the TS1 starting up again. And right before that, you'll find the stage where the host starts the lane bonding process. We see him writing the LBT bit to the dual lane mode. So by writing that bit in the router config space for both lanes, the host is enabling the dock to go into lane bonded mode. That's the first step. Second step, the host starts sending TS1s on both lanes. By asserting the LBT field in his TS1, he's directing the dock to go back to training, back into the bonding substate, always initiated by the host. We see both sides setting the LBT bit to dual lane. We see this in both the TS1 and the TS2. That's going to continue, but you can always search for the DSKU packet, which marks the end of the bonding state. And this is how the sides exchange their settings for lane-to-lane skew. It's the last unbonded ordered set in both directions, both lanes. Immediately after that, the traffic now shows LB, indicating lane-bonded operation. Scrolling further down, we see more control packets. And in the next video, we'll see how the CM configures all the lane adapters and then the protocol adapters on a device router.